Well, hi there, I'm Dr. Tom Ulrich, and I like to talk about leadership and engineering, but I also like to talk about Arduino. Hey, in this lecture, we're going to revisit the 7-segment display, and what we're going to do a little bit different this time is you'll notice there that, first of all, what you're seeing is it's going from 0 to F. There are 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So maybe in terms of looking at it, that's going to be what appears to be the difference. But in fact, the bigger difference is on this end of this board right here, where we're using this mysterious 74HC595 shift register. And what I'd like to do then is talk about what is this thing, why in the world we would want to use it, and then how do you use it. At any rate, and the plan, what I'll do, so this is what it is. I'll talk about what is a shift register, how do I use a shift register, what data do I send the shift register, how do I write the code, how do I wire it up, and then give you some evidence to see if it actually works. And I guess, I guess I kind of just did give you the evidence showing you it worked there in the thing, but I'll show you some more shots of it. At any rate, so okay, so what is a shift register? Well, basically, it's a gadget where you give it a serial stream of data coming in, so you use just a couple of wires to send a serial message, 8 bits, and then it has 8 outputs that will then, it'll hold each bit discretely per the data coming in. So let me give you a clear example of that. On the previous lecture, we were driving the 7-segment display discretely from the Arduino. So each segment of the display is basically an LED, and we had 7 pins that would drive, the display, so one for each segment. What a shift register allows you to do is you have the shift register is the one driving the 7 segments, and between Arduino and the shift register are only 3 lines: data, latch, and clock. So the idea is you conserve lines by using a shift register, because at the end of the day, Arduino only has has less than 16 discrete lines, and you want to kind of make the most of it. All right, so what is, when I say 74HC595, what are we even talking about? Okay, so there's something to know here. And this is sort of generally applicable to as you're doing digital electronics. So first of all, that 74, that references an entire family. So there's the 7400 series of semiconductors. The HC in this case is a specific semiconductor technology. There are many semiconductor technologies. This is one of them. The 595 specifies the logical function. So it turns out there's 15 or 20 variations on shift register. The 595 is one of those variations. Now, when you look at this, going back to the 74 part then, and you can kind of mix and match those 3 pieces. So for instance, the 7400 is a quad NAND. And when I say quad, what I mean is there's 4 NAND gates. So remember early in the semester I talked about the logical function of AND and NAND and NOR and all those things? Well, people make those discretely, so you can implement that with a chip. And when they say a quad NAND, what they mean is there's 4 of them in the one package. And so a 7402 is a quad NOR. Now, a 7411, for example, is a triple 3-input AND. So the triple means there's 3 of them. And the 3 input means each one of the ANDs has 3 inputs. So instead of being like A and B, it's A and B and C. And, initially the 7400 series was just all basic logic: ANDs, ORs, NORs, NANDs, XORs, and there was variations having to do with something called open collector and whatnot. And you would have these gates with 2, 3, 4, and maybe more inputs. But over time then, there are hundreds and hundreds of these things. So the 7400 series is certainly the most popular series, the most common series of digital semiconductors. The thing about these numbers is Google knows about them. So if you want to look up a 74LS08, type in 74LS08 and boom. If you want to buy a 74LS08, go to Amazon, type it in, boom, you'll get it. So these are are well understood numbers, these 7400 series. All right, so then going to the technology, remember I said the HC part is the technology. Now I'm not going to go all into the technologies of semiconductors, but broadly speaking, here's what it is. There's bipolar, also known as transistor logic. There's a lot of them are in that family. In general, those are faster. Those use a lot of power. I mean, lots more, way more than 10 times more power than the other family. And interestingly, it's sort of a constant power usage, whether it's a 1 or a 0, doesn't really matter. It's using a lot of power all the time. They can sink a fair amount of current, so you can drive more things with them. And there's a lot of examples of this. There's the F, so 74F01. You can leave out the letter altogether. 7401, that's another member of the family. AS, LS. So for instance, 74LS00 is one of the bipolar technologies for a NAND gate. Now the other category is CMOS, and what the deal there is, generally they're intended to be much lower power. So, the bipolar is uses the same amount of power no matter what you're doing. CMOS only consumes power when you change. So if you have it as a high or have it as a low and never change it, it uses just about no power. The downside is it's definitely slower. It can't sink as much current. And generally what you'll see is, the letters there'll be a C in the letters somewhere. So ours is a 74HC595, so that's a CMOS. And another example is a 74HC00. But at any rate, so that's, you'll have a class later on where you really kind of go into that. Now another thing is this device, the Arduino comes with these chips look like this. Those are called DIP packages. DIP stands for dual inline package. Notice there's a notch kind of at the front there. And notice there's a dot right by pin 1. And the pin numbers run in kind of a U shape. So by the notch, now this one, see how there's 7 pins right there on the side. So this is a 14-pin device. It's dual inline package. The pins are kind of hidden on this one, but if you look in your Arduino kit, either there, I think the 74HC595, I think that's a 16-pin device, so it's got 8 on each side, but it's the same concept. But because the pin numbers kind of run in a U, both the 1 and the 14, or the 1 and the 16, the lowest number and the highest number pin are right by that notch. And then there's that circle thing. That is actually kind of doubly saying, here's pin 1. Once you see the notch, if you have it sideways, the notch, pin 1's going to be on the lower left, but sometimes they put a dot to make it clear. The other thing to know is if you just kind of use your fingers to pull those out of the protoboard, you're probably going to bend all the pins. So what you really want to do, so if this is pin, you kind of want to get a small screwdriver and kind of very gently lift it up. Otherwise, you're gonna mess your device up. All right, so how do I use the shift register? Well, the good news is there's actually a built-in function in Arduino. It's, you don't even have to add a library. It's just part of the basic Arduino language. And here's what the deal is. So I mentioned there's 3 pins. There's latch, there's data, and there's clock. When the latch is high, the device will maintain or latch the output as that was last written. So the idea is you bring the latch low, you send your data serially, and then you bring it high, and it sort of freezes it. Now the data and the clock comprise a simple synchronous bus. So remember we did that in class where we talked about, a synchronous bus is the one where you have 2 lines. One is sort of clocking. It sort of lets you know each time there's more data, and then the other one's got the data. So it's a simple thing. And there it is. You set the latch low, you transmit your 8 bits, you set your latch high. Now here's a kind of diagram you'll typically see. And there's the data there. So what I'm doing is I bring the latch low, and then I start the clock. And I set up the data first and then clock it. And the logical question is, wait, do I transmit the LSB first or the MSB first? And because if you interpret this, depending on how you interpret this, that first one is clearly a 1. So is that the LSB or the MSB? And what the deal is on the Arduino is you can tell it. You can tell it, hey, we're going LSB first, we're going to go MSB first. And the way you do it is you say LSB first or MSB first. Literally, that's what you say. I'll show you that in a second. Anyway, you don't have to use the Arduino thing. I mean, you could take the 3 pins and use digital write, and you could kind of control them yourself. But probably using the shift out function in Arduino is a little bit easier. Here it is here. Remember, whenever you got a question about how Arduino works, you go to arduino.cc, click on the reference. And what we see here then is it takes 4 parameters. You give it the data pin, so what pin is the data on, what pin is the clock on, what bit order. And see here, it says down here kind of in the bottom, where it says parameters, bit order, you write capital MSB first or capital LSB first. You just write it right out. And then you put the value, the 8-bit number that you want to have it clock out. Okay, and so repeating myself here, this is the deal. What you do is the shift out handles the serial communication. You tell it the pin for data, you tell it the pin for clocking, you tell it LSB first or MSB first. In my example that I'm going to show you, I do LSB first. You can do it either way. Then you give it 8 bits. You got to handle the latching. So it won't do the latching. You got to do that, but it'll do everything else. All right, so what data do I send to the shift register? Well, we're going to go back. This will be a little bit repetitive with the previous lecture, but here's the deal. In case you didn't watch the previous lecture, I'll go kind of fast. You probably want to go to the previous video if it's too fast to follow. But there's the 7-segment display. I'm physically holding it on the right, and you see it's, again, a dual inline package. And you see pins, 1 through 5 on the bottom, 6 through 10, and you see how they're kind of in a U shape where the, on the left, the 1 and the 10 are both on the left. And what you got to do is you really got to slow down. When I did this, I slowed down and did this. I got out. I actually did it in Excel. I'm just using the cell shading to do the red there. But I looked at the pattern and said, okay, if I want to make a 0, I got to light up the A, the B, the C, the D, the E, and the F, but I don't light up the G, otherwise it'd be an 8. And then I did that for 1, 2, and 3. And then I did it for 3, 4, and 5. And I did it for 6, 7, 8, 9. Now that's all the same as the last lecture. Now here's the new one. I did it for A. Okay, so that one's pretty much everything but D. I did it for the B, and that's everything. It's everything except A and B. And then I did it for the C. That's A, D, E, and F. And here I did it for the D. And yeah, it's lowercase. Yeah, it looks kind of lame. But back in the day, when this is the only kind of display you had, you made do. But it was real important to be able to do hexadecimal because, so much of microprocessor work is in hex. At any rate, so there's the codes. Okay, so in the previous lecture, what I did is I showed you a technique where I really tried to emphasize a simpler software technique for those of you who have less programming skill and maybe you're uncomfortable with what arrays are. Do the technique of the previous lecture. This would be how you would more typically do it, maybe in a professional setting. And what we basically do is we set up an array with those 16 patterns that I just identified. So something to know is in the C programming language, if you put the capital B ahead of before the number, it knows that's binary. And so on that first line at line 28, what I'm saying is, okay, to create a 0, and the 2 slashes is a comment. So after the 2 slashes, that's just a note to me. Remember I said we need A, B, C, D, E, and F. So I've got the first one is A, second one is B, third one is C, and so on. And so we've got it there where you kind of see how that corresponds. And then for line 29, all we need is B and C on, so that's a 0. The 0 is the A, then the B is the 1, the C is the 1, and then C, D, E, F, G is, or D, E, F, G is zeros. And so on. So you kind of, maybe you want to slow down and study this a little bit, but that's what I did. I went through for each one, and I said, here's my pattern. So for 3, that's at line 31, and 4 and 5. And for 6, 7, 8, and 9. And then there it is for A, B, and C. A, as you may recall, is a 10. It's hexadecimal for 10. B is hexadecimal for 11. C is hexadecimal for 12. And then there's the patterns for D, E, and F. So you can slow down the video and pause it and kind of study it at your leisure. And for those of you in the class, I'm going to post the PowerPoint, so you'll have that to look through at your leisure. At any rate, so the first step is you've got to kind of create that array, and that's what our program is going to use to translate the number into the pattern you want to send. And again, if you're newer at programming and you're like, arrays, that's too much, just do the technique without the shift register from the last lecture. But especially if you're going to be an electrical engineer, I mean, lean into this. Go ahead and do this one, force yourself through it. But anyway, for the assignment, you can do it either way. All right, so how do we write the code? Well, I just showed you some of it, which is how to do that array, but now I'm going to show you the rest. So here's the 595 here, and there's on the left, see that Q1, Q2, Q3, so those are the segments. Now notice on the right, pin 15, that's Q0. We number from, those are numbered from 0. The pins are numbered from 1, but the data is numbered from 0. That's just how the world is, sorry. You see the little circle on there to emphasize, yeah, that's where pin 1 is. So I would think you'd hook up segment A to pin 15, segment B to pin 1, C to pin 2, so on. But in this, and I'll show you that more later, but in this slide, what I'm trying to show you is this is the connection between Arduino and the 595. We need 3 pins. On the 595, it's pins 14, 12, and 11. So at line 46 there in the code, what I'm saying is that's a label that says the clock, which is the pin known as SHCP, that's pin 11 on the 595, that's going to be my pin 7 on Arduino. And then at line 47, I have a label that I'm going to say the latch, which is STCP, that's pin 12 on the 595. I'm going to say that's pin 8 on the Arduino. And then at line 48, I've got pin data DS. So on Arduino, that'll be pin 9, and that's going to hook to 595 pin 14. Now, what you're experiencing, you're like, wait, pin 5 to pin 4 to, what do digital designers do? Yeah, they pretty much do this. They do just what I said. They're trying to figure out, oh, you take this device, take pin 3, hook it to that device, and pin 5. I mean, that is in essence what a lot of digital designers do. All right, so in our setup, we got to have our standard Arduino setup. You want to take each one of those pins and you want to set them as outputs because you're going to control them. Well, actually, the shift out is going to control the clock and the data, but you still have to set it up as an output. I wrote a little function here. Now what you'll notice is in the last lecture my function for write 7 segments was enormous. It was like 200 lines or something. Here it's actually quite small. So what we do is, like the other lecture at line 60, we pass the digit. So if you wanted to display a 3, you'd pass a 3. Now the first thing I do is I make sure it's between 0 and it's less than the number of digits. So I have the number of digits is set to 16, so it's got to be greater and equal to 0, and it's got to be less than 16 because it's going to be 0 to 15. So first we drop the latch line, so we say digital write, there's the latch, we say low. Then we clock out the data, we call shift out, we tell it the data's on pin data DS, the clock's on pin clock SHCP. I say I'm doing it LSB first, that array I did is LSB first. And then what I do here is I have a reference to the array and I index the array with the digit. And that'll send the right pattern. And then I raise the latch line. We're done. So what you see is with this technique, the code, it gets a little more complex in the sense of you have to be comfortable with arrays and things like that. But at the end of the day, boy, this is a lot shorter. And then for my loop, all I did there was I said, okay, I'm just going to loop from 0 to 15, and I'm just going to write a 0 and a 1 and a 2. And that's what you saw in that little demo I held up. All right, so how do I wire this thing up? There's lots and lots of wires. So here is the wiring between the 7-segment display and the 595, and what you'll notice is that looks almost identical to how you had it last time between the Arduino, but But there I have it. You can kind of study it and see where it goes. Note that there's 2 pins, pin 8 and pin 3. You're going to have to hook to the ground on the Arduino. But other than that, now you have all those massive pins that go, to the 595. So there's very few pins that go to the Arduino, but you have all these wires here that go to the 595. You see, I've got the 595 right there. All right, and here's how it looks. You kind of can see a little view there. I've got the resistors. I cut off the lead. I cut the lead short so I don't have those things flying in the air, but it does get to be a little bit of a rat's nest. Now to connect the Arduino to the 595, that's pretty simple. What we're going to do is you got the 2 grounds and you got 2 5 volts. You got to put a 5 volt on the VCC. You also could put a 5 volt on this MR bar. And then you're going to ground the OE bar as well as the ground. And then there it is. You're going to hook up the digital I/O. You saw the ones I was using. You're going to hook them up to pin 14, 12, and 11. Okay, and does it actually work? I mean, it seems to. I showed you that video. Here are snapshots showing it correctly displaying all the digits. So there's 1 through 5. There's snapshots showing all the digits 6 through B. And then here's some snapshots showing it doing C through F. So it does seem to work. At any rate, in terms of final thoughts, the technique does work. The nice thing is it uses only 3 Arduino pins. It uses even more wires than the discrete approach. So it's, it's a lot of wires. It requires a little more programming skill. However, it does, it does conserve the Arduino pins, and that's probably the main reason you'd want to do it. The other thing is, if you want to use there's another 7-segment display in your kit that actually has 4 of those. And what you'll find is you cannot do that one discretely. There simply are not enough Arduino pins. But what you can do with this shift register is basically have 4 latches, 1 for the first digit, 1 for the second digit, 1 for the third, 1 for the fourth. And what you do is you write them in succession real fast. And if you do it fast enough, you can't even really see that really the one's on only a quarter of the time. If you do it fast enough, it just appears to be a little bit dimmer. At any rate, hey, thanks for listening. If you want to go to see more videos by me, I've at TomUlrichConsulting.com. I've got them on both Arduino and also on Leading Engineers. If you want to find more videos on YouTube, you can search on Dr. Tom Ulrich. At any rate, if you don't mind, you give me a little like, maybe subscribe. If you leave a comment, I'll answer you back. At any rate, thanks for listening, and we'll talk to you next time.